Okay, hello, welcome everyone. Thank you for joining the RecSys 2020 session on evaluating and explaining recommender systems. My name is Kim Falk and I'm going to be the chair for this session. Before we get started, I should remind everybody that if you have questions for a particular presentation, please go to the VOVA agenda entry for that presentation. If you're on the desktop app, the live video streaming will keep playing on a floating window, so don't miss anything. So you won't miss anything. We have a tight schedule here, so I will encourage you to follow up with the speakers and continue discussion after the session on VOA. Without further ado, let's get started. The first speaker tonight is Mesut from Delft, and he's going to talk about group recommendations.
Thanks, Kim. So, welcome to the paper presentation for ensuring fairness in group recommendations by rank-sensitive balancing of relevance. My name is Mesut, and this work has been conducted while I was a research engineer at TU Delft. This is a joint work with Dr. Debiased from University College Cork and Dr. Nava Tintarev from TU Delft. There are many scenarios where we want to recommend Does it work now? Okay, I will start from the beginning. Okay. Again, welcome to the paper presentation for ensuring fairness in group recommendations by rank-sensitive balancing of relevance. My name is Mesut, and this work has been conducted while I was a research engineer at TU Delft. This is a joint work with Dr. Debiased from University College Cork and Dr. Nava Tintarev from TU Delft. There are many scenarios where we want to recommend a set of items to a group of people rather than to an individual. And for group recommendations, one objective is to recommend an ordered set of recommendations such that each individual recommendation is relevant for everyone. And a common way to do is to select items on which group members will agree on using so-called aggregation strategies. However, aggregation strategies that select items independently of each other cannot guarantee properties such as fairness that apply to the set of recommendations as a whole. We can illustrate this problem by using a simple example. Consider a group with 3 people and assume that there are 5 candidate items to be recommended to this group, and our goal is to recommend top 3 set of items. We run a recommender algorithm to predict the relevance scores of each candidate item to each group member and assume that an item is relevant to a group member if the predicted relevance score is greater than or equal to 4. Now let's say we use 2 of the aggregation strategies that are called average and least misery to recommend top 3 to this group. Average strategy computes the mean ratings of the group members as the relevance score of items to the group, whereas least misery strategy takes the minimum rating as the relevance score of the items to the group. Now, if we look at the top 3s of both average and least misery strategies, what we see here is that the circled group member cannot find any relevant item to her, unlike the other group members, which is unfair to her. This is the kind of unfairness that we try to address in our paper. Even if each individual recommendation is found in a fair way, since they are found independently of each other, the generated top 3 is unfair to the circled group member. So with average and least misery in our mind, let us ask ourselves what a fair top-N group recommendation might look like. First of all, a fair top-N group recommendation must seek to balance the relevance of the items in the set across the group members. What do we mean by this? Remember the output of average strategy from the previous slide, which is the 3 items in the green circle. If we look at the total relevance score of those items for each group member, we can see that for the first group member, for example, it is 13.5, which is the same for the second user. However, for the third user, we can see that it is only 8. And we can say that other group members' total relevance scores far exceeds circled users, which is unfair to her. Now let us look at another top 3, which differs from the previous one by only the last item. What we can observe here is that the total relevance of the items in this set, the relevance is more balanced across the group members. And in our work, since the order of the items in the set is important as well, the top N group recommendation will be even fairer to a group if it seeks to balance the relevance of the items across the group members for each prefix of the top N. What do we mean by this? Now consider two different permutations of the circled three items, for which the first item is the same. What differs is the position of second and third item. Now, if we look at the total relevance of the items at each prefix, since at the first position the item is the same, the total relevance will be the same for both permutations, and it will only differ at the second position. So if we look at the total relevance of the first and second item taken together for each group member, what we observe here is that for the first permutation, it is more balanced compared with the second permutations, and the reason is the third user. So this is the rank-sensitive balancing of relevance that we talk in our paper. And again, if we go to the third position, since the items are the same for both permutations, the total relevance score will be the same for both of them. So this leads us to our formal definition of fairness, which is a top N group is fair to a group if the relevance of the items is balanced across the group members for each prefix of the top N. In other words, the first item in the top N should, as far as possible, balance the interests of all group members. The first two items taken together must do the same, and so on the first three. Based on this definition of fairness, in our paper, we provide a greedy algorithm that we call group fairness-aware recommendations for finding a top N order set of group recommendations that satisfy our definition. Current fairness-aware group recommendation methods do not define fairness in a rank-sensitive way the way that we do, although some achieve a degree of rank sensitivity through the greedy algorithms. Without going to details of our method due to the time limitation, I will talk about the experiments. In our experiments, we used two datasets, one from each of the movie and music domains, and we created synthetic groups of different sizes and different group types based on the similarity between group members' interests that we call random groups, similar groups, and divergent groups. This leads us, and we use 10 evaluation metrics adapted from literature to measure the performance of our approach and the other approaches from the literature. This leads us to 210 cases per data set, and we compare the performance of our approach GFAR to 5 approaches from the literature, which are average and fairness aggregation strategies, and 3 of the recent fairness-aware group algorithms that are called XPO greedy, LM, and SP greedy. If we look at the summary of the experimental results for 2 datasets out of 420 cases, we can see that for 43% of the cases, GFAR is the best performing approach, and the difference between GFAR and the second best performing approach is statistically significant. Again, for other 29% of the cases, GFAR is the best performing approach. However, the difference between GFAR and the second best performing approach is not statistically significant. And for only 18% of the cases, any of the other approaches is the best performing approach, and the difference between best performing approach and GFAR is statistically significant. Finally, for the remaining 10% of the cases, again, any of the other approaches is the best performing approach. However, the difference between the best performing approach and GFAR is not statistically significant. In the experimental result, we also observed that it is more difficult to find fair top N recommendations for groups in which the members' interests diverge. In other words, it is slightly easier to find fair top N recommendations for similar groups compared with divergent groups. And we also observed that it becomes more difficult to find fair recommendations as the group size grows. For example, it is slightly easier for group size of 2 compared with group size of 8. To conclude, in our paper, we present a novel definition of fairness for group recommendations that we call GFAR. And GFAR is rank sensitive in the sense that it defines top N as fair if the relevance of the items to the group members is balanced across the group members for each prefix of the top N. And experimental results on 2 datasets show the effectiveness of GFAR. For the future work, we are planning to apply GFAR to NIV domains. And the most importantly, we are planning to conduct user trials to test GFAR's effectiveness on real groups, since gaps exist between serving recommendations to real-world groups and synthetic groups. Thus, the assumptions that we make may not be valid in practice. And finally, we are planning to investigate variants of GFAR, such as allowing user-specific weights. This is the end of my presentation and some personal news. I'm currently looking to find a job. If you try to contact me, you can look at my Hoof profile. Thanks for your attention. If you have any questions, I will be glad to answer them.
Thank you very much, Mesut. There are a few questions which disappeared for me. Okay, yes. So there is a question from Ivan. Could any other group-related properties potentially influence the extent to which fairness could be seen differently across different members? For example, consensus, disagreement, positions between members.
Yes, I think it can, but in our paper, what we do is basically our definition of fairness. We consider each group member equal without looking at this, consensus or disagreement. Currently, we are working on, for example, alternative of GFAR, where we look at, for example, based on different scenarios, for example, giving different weights to the group members. One example is, for example, we realized that for the group members that has more preferences in their profile, the algorithm tends to favor them more compared with the others. I don't know if this answer his question.
I think so. Then there is another question from Amifa. How the relevance is measured across the group? Okay,
so the details are in the paper, but basically what we do, we are looking at the probability of the relevance of an item to a group member. Basically what we do, first of all, we compute individual tapan for the group members. And then when we apply our algorithm and we create the group tapan, what we look, if we look at if a recommendation in the tapan group recommendation is in the individual group recommendation, then it is like based on the rank of the items, it is kind of discounted. That is one way to measure relevance. And another way that we tried but didn't work quite well compared with this one was using the predicted relevance score of the items. For example, we are running a baseline algorithm matrix factorization. For each candidate item, there's a relevance score, and the relevance score for the items were based on that scores.
If I might also add, we look at a large number of metrics looking at how well it performs across the group members, right? And some are min-max, some are average. So we do actually discuss that in quite a lot of detail in the paper if you do want to look at it.
Yeah, thanks, Nava.
I think we have time for one more question from Xu Yung. Could you explain more about the fairness metric definition? I think maybe you did that already.
Fairness metric. I mean, in our paper, we have the formal definition of fairness, which differs from the previous approaches by the rank sensitive of balancing, right? Other approaches, for example, just look at the sets without looking at the ranks. And they say that a tapan is fair to a group if it has one relevant item for each individual group member. But in our paper, what we focus on for each prefix of tapan, we should look at fairness in here. But if the question is asking about how do we measure fairness, we use 10 different metrics and the details are in the paper. And like Nava said, for example, for NDCG, we compute NDCG for each group member and we look at the mean and we look at the minimum of NDCG and we look at the min-max ratio. So for each metric, there are 3 variations that we look.
Okay. Thank you, Mesut. I don't think we have time for any more questions.
Thank you.
Please continue submitting your questions to the QA interface on Voa if you have more questions. And thank you once again. Okay, so, and then the next speaker would be in Huang from University of Amsterdam, talking about keeping dataset bias out of the simulation when you work with reinforcement learning.
Hello, everyone. So welcome to my presentation for our full paper, keeping dataset biases out of the simulation, a deep bias simulator for reinforcement learning-based recommendation system. And my name is Jing Huang. This is a joint work together with Harrie, Oosterhuis, Maarten, Delhaize, and Herke van Hoof. So we just jump to the main contribution of our paper. So we find we find the existing simulators allow offline IL-based recommendation learning, but they ignore the bias present in logged data. So we introduce a solution of debiasing simulators to mitigate the effect of bias. And we also find these simulators haven't been evaluated based on the performance of their produced policy, despite a well-performed policy is the ultimate goal. So we introduce a novel evaluation method and evaluate the effect of the bias on the final policy perform of a simulator. So where the first two contributions can be applied to any reinforcement learning-based recommendation simulator, we combine them in a newly proposed simulator for offline learning and evaluation. So we called it so far for short. Before I present our work, I would like to start with a brief introduction of two backgrounds. The first is reinforcement learning-based recommendation system. So the left figure displays the typical flow of IL for REC. A state is historic interactions of a user who is about to receive a recommendation, and an action is an item being recommended by the policy of the recommendation system. The reward is implicit or explicit user feedback. The goal of IL for REC is to maximize the cumulative rewards over multiple sequential recommendations. Although the IL for RECs have so many advantages, but it brings risk when applied online. An alternative to online experimentation is provided by the simulation-based experiments. Here we show in the red figure, the user's feedback on atoms is simulated according to the logged data. So the second background is interaction bias in logged data. We take the positivity bias as an example. So this positivity bias occurs because the user rate the atoms they like more often, and this results in positive feedback of the training set be overrepresented. As a result of this kind of bias, the logged data is not uniform randomly observed. The missing slot in the rating matrix are missing not at random. So formally, the MNAR is often modeled by separating the probability of observation and the probability of a rating. If every rating is equally like to be observed, so there is no bias and all the users and atoms are equally represented. When the positivity bias is present, the atoms that receive higher ratings are more likely to be given a rating. So without the correction, the bias may affect the rating prediction and further influence the IL for REC simulators and their produced policy. Here we'll take a very simple example to estimate the average rating of an atom. And the naive estimation is simply the average of the observed ratings. But in expectation, we can see the naive estimate is affected by the observance probability. If there is no bias, the estimate is correct in expectation. But when the positive bias is present, the estimate is expected to overestimate the true average ratings. So we want to debiase a simulator, and we focus on the simulators with the predicted user atom rating metrics to model user preference and a user choice model to simulate user feedback. As discussed in the background, the logged data suffers from the interaction bias. Then the predicted user atom rating matrix is also biased. The simulator is biased, and the final produced policy is also biased. If we unfold this flow, we got the second figure. So this poses a problem for IR4REC, since the simulated user feedback shouldn't be affected by the way a dataset was logged. As a solution, we proposed the immediate bias mitigation step, IBMIs, between the logged data and the learned prediction model. So we hope it can minimize the effect of bias to reach the subsequent steps, including the final produced policy. Then we have the IBMIs can apply any debiasing method. Here we use inverse propensity scoring. The key idea of IPS is inversely weighting the logged ratings in loss function, and this can be proved that the expectation of IPS loss based on the logged data provides an unbiased estimate of the full information loss. Then we have a question how to evaluate if the proposed IBMIs mitigate the bias from affecting the produced policy or not. So the existing work has evaluated the IR4REC simulators by comparing their simulated feedback with the logged user feedback. It's shown in the left figure. The downside of this evaluation is that they don't consider the performance of the policy learned with a simulator. And we consider this aspect. So we propose an offline evaluation method and based on the performance of the final produced policy. So our evaluation method only requires a sparse set of missing complete at random ratings, which can be gathered on randomly selected atoms. And this evaluation method consists of the following 4 steps. First, training a policy with a simulator, using a simulator with IBMIs on MNAR data. So this will result in a debiased policy. Second, we train a policy using an identical simulator without the IBMIs on the dataset. So we have a biased policy. Third, we create the identical simulator with based on the MCAR ratings, because the MCAR rating is unbiased, so this simulator is also unbiased. Finally, we deploy the debiased and the biased policy in the unbiased simulator. By comparing the cumulative rewards of the debiased and the biased policy, we can see if the IBMIs truly removed the effect of bias or not. So recall the flow of the IR4REC with a simulator showing the figure. So we show our newly proposed simulator so far. So it's consisting of the 2 components. The first is debiased user atom rating matrix produced by using the IBMIs with applying the matrix factorization with the APIs. And we also have the user choice model to simulate user feedback and provide the updated state and the immediate reward to the recommendation system. So our experiments aim to answer 2 main research questions. First, that the interaction bias in logged data affect the simulator. Second, can the IBMIs mitigate the bias or not? So the left figure shows the learning curve of the 2 policies. One is learned with a biased simulator, the naive thing, and the other is learned with a debiased simulator, ours so far. So we can observe that the cumulative number of clicks for policy learned with naive simulator is consistently higher than so far. It's a little weird because the so far is our method, but it's noteworthy that the learning curve are based on the number of clicks receiving received during training, so they are unreliable estimate of actual performance because of the bias. So the right plot shows the evaluation results of two policy, and the policy resulting from using so far outperforms the one using naive thing. So this outperforming of policy learned with our so far can answer the second research question, yet the IBMS can mitigate the bias. And the reversal of the learning curve and the evaluation results can answer the first research question positive. So in our paper, we analyze we analyze the effect of the bias on the IL-REC simulators and their produced policy, and the proposed immediate bias mitigation step can mitigate the effect of bias. And we also propose a novel way of evaluating the effect of bias on the final produced policy. And we also provide so far the first simulator for IL-REC with correcting for bias. So in future work, we will consider the effect of the interaction bias on the simulator for multi-atom recommendation scenario, because in this case, we only consider the single atom recommendation scenario, and we will consider more widely relevant recommendation task like the ranking task with using the implicit feedback. So that's our work, and thanks for your listening.
Thank you, Tsing. It was very interesting. There is a few questions. There's one asked by you. Are you applying IPS to a single entry or to a sequence of entries? If the earlier, could bias leak in from sequential dependencies? If the later, how are you keeping variance under control?
Actually, we just use IPS on the rating prediction task, because in our case, we consider the explicit user feedback, which can show if the user like this atom or not. And so, I think we will consider applying the IPS to a sequential recommendation. I'm not sure if it's means the sequence of entries or not.
Okay. There's another question asked by Bob. Did you also look into other metrics, such as the level of personalization or amount of exploration behavior when using SOFA relative to naive policy?
For now, we only consider the cumulative numbers of colleagues when we use when we learn policy, because the things we carry is reinforcement learning-based recommendation, and normally we use a cumulative number of clicks as evaluation metrics. But I think it's a very good idea to consider the personality or other. We will consider it in our future work.
Sounds good. And last question. How did you deal with missing data in the interactive evaluation?
Yes, it's a very good question. So because the missing a slot in the tested data, so we give the two solutions to deal with this the missing slot. So one is we only let the policy to learn to evaluate on the atoms which the user have the ratings on this atom in the test set. The other is we generate according to the test set, so that's we have the pseudo ground truth, not the real ground truth. But it's not the perfect solution. So we just give the two solutions. We expect yeah, we expect that there can have a better solution.
Okay, thank you very much, Jim.
Yeah, thanks.
Then, yeah, there is a joke that I keep wanting to say, but it never really comes to the right point. But Nava suggested that you should say, if you like this talk, you might also like the next speaker, who is Pablo Castellis from Universidad Autónoma de Madrid.
Thank you, Kim. I hope so. So hello, everyone. I'm Pablo Castells from the Autónoma University of Madrid. And this is joint work with Rocío Cañamares on better understanding the effects of picking different sets of target items in offline evaluation. This is a particular aspect in designing offline experiments that has not been paid much attention. And we want to better understand the effects of this setting, what the options are, whether they can affect the result of an experiment, and if possible, some hint as to how to best handle this. So let me start by explaining what we mean by target items and giving some context. So imagine you have two recommender systems, A and B, and you need to find out which one is better. And for whatever reason, you cannot afford an online A/B test, so you run an offline experiment. In an offline experiment, you collect some offline data with observed user activity. The data involves a set of items that your evaluated systems should recommend. And you typically split the data into training and test subsets, which you can do in many different ways. Then you pass your training data as input to your evaluated systems. And then for every user, you ask your systems to rank the items. You compute some metrics on the rankings using test data, you compare, and you come to some conclusion as to which system seems better. Your goal in offline evaluation is that it represents your real scenario as well as possible. And you may be aware that this is not necessarily easy, and it's actually an open problem. But you also want your experiment to be consistent and comparable to other offline experiments, so that, for instance, as a community, we can build on the work of each other. So you need to be careful with vanity tests in how you design your experiment. So with that in mind, there is a particular design detail that is often implicit in offline evaluation, and it's the selection of the target items. Target items are the items you ask your evaluated systems to rank, and this is not necessarily all items. So why would you take a subset instead of just all items? To begin with, in most cases, you don't want your evaluated systems to recommend items that have training data for the target user, so you don't put those on the rankings. So in practice, you usually take a subset of target items, even if you didn't intend to. And then it has become increasingly common to take smaller sets to reduce the cost of experiments, or maybe for other reasons. So the question is, does it matter? Can you still rely on the results if you are using fewer items? Or maybe, who knows, would you get more reliable results by taking fewer target items? First of all, what are the options when picking target items? Well, first, we may consider that any sensible option should include at least all items with a test rating and no items with a training rating. So in terms of the number of target items, the options would be how many unrated items we include in the target set. And we can go from all unrated items, which is the typical option in the literature, to no unrated items, and any number of unrated items in between. So now the important question is, can this setting affect the result of evaluation? Well, the answer is certainly yes. And it's easy to see with a very simple toy example like this one. So let's say we have these two rankings, and with all our unrated items, A is better than B because A returns one relevant item in the top two, represented in green, and B returns just two white unrated items. If we now remove unrated items from the rankings, you can easily see that now B is better than A, because now B returns two relevant items in the top two. Now the question is this just an artificial example that I came up with, or would we observe things like this in experiments with real data? So let's check. So let's run a typical offline experiment. Movie length 1 million, 8 systems, random split, precision at 10. And let's evaluate with all unrated items in the target set. This is what you are seeing on the left. And then with no unrated items, and you see that on the right. It doesn't really matter which specific algorithms we evaluate here. We see many interesting observations, but let me focus on the most important ones to make my point. For that, let me just show you the order of algorithms from best to worst in precision at 10. So this is the best algorithm in the first setting, like some version of matrix factorization. A different version of matrix factorization is the best in the other setting with no unrated items, and then random is the worst in both of them. But you can already see that the order is not the same, the order of the best to worst system. We can see this better with lines. So each line is a system, and each pair of crossing lines represent a disagreement in the comparison between a pair of systems. And you can see a considerable number of disagreements reflected by, in fact, a very low Kendall correlation. So this is something to worry about, because we would come to totally different conclusions with different target sets. Even more important, the disagreement is not by chance. There is actually a systematic bias. Let me explain this. For instance, recommending popular items gets better results when evaluated with many unrated target items. The same happens when taking into account unrated items in the objective function of your algorithm when training your model. On the other hand, taking few target items favors models that ignore unrated items when training, and the recommendation of items with a high average rating as a particular case. And then the parameter settings that work better in with each target size are completely different. So all this is worrying because your experiment can give contradictory advice depending on the number of unrated items that you take. The tricky question is, which results should we trust? Like, maybe should we use all unrated items every time, or how would we know? Okay, so here's an idea. Since we want our experiments to match online evaluation, let's compare to unbiased evaluation. Even if we don't have a running system, we can use a dataset like Yahoo R3 that has both random and non-random ratings, so that we can do both biased and unbiased evaluation and compare. This is the result. In the line graph of system rankings, we now put unbiased evaluation in the middle, so we can check how much the big and the small target sets agree with unbiased evaluation. We see a good number of crossing lines in both settings. Perhaps a bit more here on the right when we use no unrated targets, but taking all unrated targets on the left is not that good either. So given that the extremes do not seem to match unbiased evaluation that well, we might wonder whether perhaps some number of unrated items in between might work better. So let's check. So now in this graph, we are checking the Kendall correlation over the whole range of target sizes in the x-axis, from all unrated items on the left to no unrated on the right. You see that indeed there seems to be some better points in between the extremes. In particular, it seems like about 100 unrated items might be a reasonable choice. So this could be a good criterion to find what a suitable number of unrated items can be. However, how about any usual data set that doesn't have random ratings, so we cannot do unbiased evaluation? Like, how do we know what's a good target size in movie lens? Okay, so here's an idea. Let's check the discriminative power of the experiment. And this means the capability of evaluation to distinguish between two systems with some certainty. As a way to analyze discriminative power, we check the number of ties in an experiment. The number of ties is the number of users with the same value for precision at 10, in this case, for some pair of systems. So we show this with a blue curve, where lower is better because it's fewer ties. We see some correspondence between the green and red curve. So the blue curve, the number of ties, is almost a mirror of unbiased correlation. Both suggest a similar ideal number of unrated targets. So minimizing ties could be a good criterion to settle for a target size in movie lens. On the other hand, tie analysis would confirm that many or very few unrated items may neither be the best option in general, because they both produce many ties. So why is that? On the one side, with very few target items, the number of possible rankings becomes very small. Systems have a hard time producing a different ranking from each other. On the other extreme, with many unrated items, relevant items get kind of buried in the pile. So it becomes increasingly difficult for the evaluated systems to rank them in the top 10. More and more users and systems get zero precision, which means more and more ties. So we have analyzed discriminative power in terms of ties. But the usual tool for this are the traditional statistical significance tests. So we check those two. For this purpose, we sum the p-values of a t-test for all system pairs in each experiment, and we show this with the black curve. We see it is less clear than the blue curve. It would seem a bit noisy, a bit shaky, especially here in movie lens, and the correspondence with unbiased evaluation is not as clean. In fact, it is actually known that the statistical tests don't handle ties very clearly. So you may have many ties and you don't necessarily get high p-values. So the number of ties seems a clearer reference for our purpose than traditional statistical tests. Finally, small targets have an additional weakness, and it's that they can cause incomplete rankings. Some algorithms may not be able to rank as many items as the metric cutoff requires when the choice of target items is too small. This can mess up evaluation seriously if we don't realize it's happening and we don't handle incomplete rankings in a consistent way. And this is an additional cause for disagreements when using different numbers of target items. So to conclude, target items do indeed make a big difference in the outcome of comparative evaluation. The difference is biased differently for different algorithms. The weakness of taking few target items is that it gets difficult to produce different rankings. And on the other hand, you may get incomplete rankings. The weakness of taking many target items is that they may cause higher exposure to non-random biases, and it's also more difficult to produce metric values greater than 0. So in both cases, we have a loss in discriminative power. The sweet spot in target size that we have found may reflect a balance between these weaknesses. Finally, in our analysis, we find that the number of ties can be a useful discriminative power measure, even beyond our current purpose. It is smoother, more stable than p-values, easy to understand. In our case, it seems to match correlation with unbiased evaluation, and so it can help choose an appropriate target size. So to conclude, we don't think all questions are answered by your research, and more research is needed. In particular, sampling target items, in fact, implies adding a pre-filter for recommendation algorithms, and this perspective could be further analyzed. Another question is, do our experiments with Yahoo actually match online evaluation? This could be answered, of course, with actual online evaluation, and maybe further online data sets with missing random data. Finally, let me mention 2 papers that were just published at KDD last month. They address the exact same problem as we did, but focus on different angles. And our findings are complementary and confirm each other on several points. So if you're interested in this topic, I highly recommend reading them. And with this, I thank you for your attention, and I'll be happy to take your questions.
Thank you, Pablo. And yes, we do have a few questions. The first one is asked by Bob.
Yep.
How would this turn out in a context without a positive/negative ranking, but things such as viewing time, where any time is greater than not viewing at all?
Yeah, so I guess you mean when you have data where you don't have, you have, only positive feedback. In this case, if you use too few unrated items, the problem gets worse. So it's like, let me just get back to. Here you would be like really bad, because you cannot even evaluate with 0 unrated items. You need some unrated items. Otherwise, all systems would get like perfect precision, because they would return only relevant items. So the system gets worse. In the extreme, it doesn't make sense. But even if you get near the extreme, the situation is like increased. So yeah, that's a good question. All the analysis is valid. It just gets even clearer in the extreme where you take too few target items.
Okay, and we have one question more from Derek. How do your findings impact on evaluation, such as the 1,000+1 evaluations?
Yeah, so 1,000+1 is exactly. So so actually that's I would say that's the idea that started all this that motivated our research, in fact. So I think Yehuda Koren, I believe, was the first to apply this technique in 2008 in a KDD paper. And so that's a particular case in our analysis. It's a target size in between. So in practice, so our analysis would confirm that this could be a good setting. So 1,000 plus 1. There is a nuance is that when you do the +1 approach, you are breaking your your test ratings for the target user into different rankings. We have not addressed that in the paper, but we have found out that this is equivalent to just creating a single ranking with all the with all the relevant items contained in this ranking, and then the 1,000 non-relevant items. So this actually intends to understand whether that would work. Our findings would confirm that it could be okay to evaluate with that kind of setting, because it's something in between, not taking all unrated items, but taking a sufficient number of them.
Okay. Thank you very much, Pablo.
Sure.
I just want to remind you, everybody, that you can continue the discussions in the QA interface and more. And now for the next speaker, who is Marilena Kyrakidi from University of Athens. Here you go.
Yes. Okay, let's see. Pablo, can you stop sharing your screen so I can, share mine? Thanks.
Sorry.
Okay. I didn't know. I thought, I could stop it myself, but it said I can't. Let's see. One moment. Okay. Okay. All right. So hi, I am Marialena Kyriakidi. I currently work at Google Research in London, but the work that I will be presenting here today was done with my colleagues at the University of Athens, and it is called Recommendations as Path Explorations. Now, first, let's talk a bit about motivation. So recommenders are becoming the core in many industrial systems today, and as a result, their usage increases, and they are becoming more and more diverse. So we noticed this diversity and we classified it in three main aspects. The first one is the information space, which practically means that you have data that is heterogeneous, interconnected, and they regularly grow in size. Second is diversity in the recommendation goal, which means that what is being recommended and to whom may change, it heavily depends on the current application needs. And lastly, there are the recommendation mechanisms that are used to generate the recommendations, and that can vary from conventional collaborative filtering techniques or deep learning and many, many more. Now, all of this has led to an enormous number of recommenders that seem different, and they are actually tailored solutions for very specific tasks within a specific domain and a specific information space. And I deliberately used the word specific 3 times. So now, as you can see, all of this denotes a lack of methodology towards recommendations, and it induces a lot of complexity. This complexity can be quite problematic because it is true that you have many solutions that are very good, but these solutions cannot be easily reused. They cannot be easily generalized or adapted to different or novel problem settings. There is a lot of replicated effort going on. Even the optimizations can be handcrafted and case-based in most cases. And also the experimental comparison and evaluation is a bit troublesome as well. So what we did is we tried to look at the recommendations in a different way. And we argue that most recommendation approaches can be abstracted as a graph exploration problem. We formulate the whole methodology around this argument, which you will see. So we proposed Regraph. Regraph is a graph theoretic approach to recommendations, and it consists of a data model and a computation model. Now, Regraph is a uniform model, and it consists of a small set of abstractions. These abstractions are very useful because we can capture different recommendation elements with them. We can explore the heterogeneous connections. It facilitates the design and evaluation in general, and it also enables scalability whenever that is possible. Our approach is actually inspired by the success of data management systems, and we think that this is a very good step, first step anyway, towards recommendation management systems as well. But now let's look a bit into the model. So first one, it's the Regraph data model. So as you can probably see, this is an example, and the data model is a graph. The nodes here are entities that can be recommended. They are relevant to the domain. They can be recommended or they can receive recommendations. The edges can be of multiple types. They can denote domain structure. They can be a state, attitude, or any kind of preference in general. Also note that in the schema, there are on the top, there are some blue node edges, and on the bottom, there are some gray ones. So we have the blue ones correspond to schema information, while the gray ones are instance information. We use both of them in the same model. And now let's use this graph to run a small example. We will not compute anything, but still. Let's suppose that you want to answer a recommendation question. So does user Johnny wants or should go to a restaurant named Kenko? So when you use Regraph, any kind of recommendation question transforms into a reachability question between two nodes in the graph. So any kind of question, we transform it as, is there a path between these two nodes? And this is the abstraction that I was talking about. So if you change the start and end nodes, you kind of like change the recommendation question and the problem as well. Keeping in mind that about abstraction, this is the formal definition of us doing recommendations as a path problem. I don't really want you to read any of this. I just want it to be fancy, and I want you to keep in mind only those three arrows, because these three arrows are the computational model for Regraph. So we need these three operators because they are the one that we will use to move on the graph on the model that we previously defined. They were inspired by path algebra, and they are tailored to the recommendation model. So here they are in more detail. So the first one is con, and it derives this red edge that you see here. It is used to traverse consecutive edges. The other two that you can see here at the bottom, they are called ag and fuse, and they are used to combine multiple edges between the same start and end nodes into one. They seem the same, but they are slightly different because ag has edges that have the same labels, while fuse have very distinct labels. They are different. Also, I will put it here as a side note. These operators can exhibit mathematical properties. The full list of the properties is listed in the paper if you want to go and see. But I want you to remember that fact because we will use it later on to see how it can support optimization techniques. So if you want to write a recommendation algorithm, you actually write a combination using only these three operators and nothing else. You will do that by using the query language that we also offer. So here it is. There are some extended data log-like rules, and you will write a recommendation algorithm using this format. Now, this program will be communicated to a graph engine that runs on top of it. So Regraph is actually written in Java, and it runs on top of Neo4j. I don't know if you know it, but it is a very powerful graph engine. Could be any engine, really, but we just chose Neo4j because it is very popular and well documented. And now, very fast, I will briefly go to the benefits. So why would you want to use such a framework? So we figured that since a recommendation process consists of mainly two parts, so you have user-system interactions only, we want to benefit both the user side and the system side. So the first two benefits are expressivity and usability, and they benefit the user. And the last one is processing speed, and that benefits the system. So we achieved expressivity due to the abstractions in both the data model and the computational model. The abstractions in the data model can capture the different heterogeneous recommendation space from the different applications. And the computational model has the abstractions there, can capture the different algorithms that you can use, but using the same uniform logic with only these three operators. And we also have some in the paper, we have some algorithmic families that we use the model to model it with. You can go and check it out if you like. And this is it about expressivity. Moving on to usability, this is quite easier to see. So because the query language that it uses is declarative, this helps the designer to focus on the logic of the algorithm rather than on the implementation. The code needed is shorter and it is easier to understand. It's not something that we only say. We did the pilot study with users at the university and they helped us. I hope they were right. And now lastly, it's the processing speed. So as I said, Regraph is implemented on top of a graph engine. Now, graph engines are good are great for interlinked data scalability. And what's more great for them is that they have an optimizer that comes with them. And if you remember the properties that I mentioned that the operators had in the previous slide, I will show you in the next one how the optimizer in the engine can use these operators, these properties to increase the speed. So let's suppose that you have a user coming in and the user writes using our query language, and this program is transformed into an execution plan. The execution plan is the one that you see on the left, the initial one. This is what the user wrote. This is a nice intuitive plan, but it's not the best one. So here comes the optimizer, and given the rules, he can transform this plan and create the next one, which is better and faster. Maybe not that intuitive, but that doesn't matter. So we also check this with experiments. We used the Yelp dataset because it's one of the richest semantically datasets that we could find. And we also try to pick algorithms from different parts in the literature to showcase the expressivity as well. So you will see that below we also have a packaged recommendation algorithm along with content and collaborative and social recommendation ones. I cannot go into much detail, but you see three main columns here. Regraph 1 and Regraph 2 are the first two, and they are implemented with our language. And the third one is Cypher, which is implemented with the native language that Neo4j supports. So mostly here, the main column, the middle one wins, and it's always better. And the main column is an algorithm produced not only by our framework, but by the optimizer that he produced. And I think that's it. Yes, this is it. So I provided everything I could tell you about this framework. I hope you liked it. And future work, there is plenty. Apparently, there are like many directions. I cannot even begin, but we can discuss it offline if you like. Thank you. And stop share, I guess. Let's see.
Thank you, Marilena. There's a few questions for you. We have time for a few, yes. Did you encounter problems of supernodes due to inherent popularity biases in user behavior? If yes, how did you solve it in Neo4j? Example, one artist listened by many users. Sorry.
I'm sorry, can you repeat the question because it was a bit big, or can I see it because I kind of like missed it?
Okay, so did you encounter problems of supernodes due to inherent popularity biases in the user behavior?
We didn't, but we mostly used some experiments on Movie Lens and on Yelp. So I don't, we didn't encounter many of the issues that you mentioned, but I will keep an eye for it.
Okay. How do you tackle cold start problems?
How do you type cold start problems or handle?
How do you handle?
So the thing about the framework is not really about comparing it, using it for a simple, for a specific recommendation algorithm. The thing is that it is a uniform approach, and it kind of provides you with a very concise set of operations to express many algorithms. It doesn't matter if it's used for cold start problem or for collaborative filtering or whatever algorithms. It just tries to express in a single way the most algorithms that it can, so that it can take advantage of optimizations using the graph engine. So it's not about a specific algorithm. So it can express it any way you want it using these operators, but this is not the point of this work.
Okay. I don't think we have time for any more questions. Again, just a reminder, you can continue the discussions on the QA interface on VOA. And now it's time for the next speaker, who is Darius Afka from DISA.
Hi, so let me share this. So hi, I'm presenting a work done at DISA Research with Romain. Not changing. Okay. So to have a bit of context, interpretation is a vast field, and for a recommender system, there have been a substantial work on finding ways to explain and justify recommended items to users, since it has been shown to improve users' forgiveness for bad recommendation and their overall trust in a recommender system. And a little more understudied branch of interpretation is the analysis of how a model actually makes its prediction, which has many applications ranging from debugging a model to ensuring recommendation fairness. But more than this, generally being able to relate a model inputs to its outputs tells a lot about the data we are handling and can be used to interpret implicit signals. So typically at a music streaming company like Deezer, we try to model user intents and tastes, which are highly subjective, especially for music, and only based on weak indicators that only implicitly translate their taste. So for instance, if we look at a user listening session, it is straightforward to create models that will predict and anticipate the tracks that you're going to skip and the one that you will listen to. But it's not obvious to additionally interpret if this is because you didn't like the music, and hence we may adjust your recommendation tastes or just shuffling through the catalog looking for new content, and hence we must adapt the type of track for recommending or something completely different. And one way to solve this is through the attribution task, meaning that it's more general than just interpreting skips for Deezer, but mean that we want to know what input feature was the most salient to make a prediction. So formally, starting from a supervised prediction task with a random input variable X that we try to map to a target variable Y through a parameterized family f theta. The attribution task consists in adding a random set of indices S and optimizing according to two contradicting objectives. So first, being able to predict Y from the input now restricted to a set of indices S, and that while having S as small as possible. The problem, however, is that for a n-dimensional input, we have 2 to the power n candidates for the restriction S, meaning that if we had an infinite computational power, we could train many models, each restricted on a specific subset, and we solve the attribution by selecting a model with low error value and small domain dimension. But as you can guess, this is typically NP hard, and there are many other issues at stake, as dealing with overlapping subsets, ensuring the unicity of the solution, and of course, not degrading the prediction performances. So that's why many methods view attribution as a secondary task. So they solve a proxy task or resort to variational approximations to avoid this prohibitive computational costs. And another branch of interpretability methods, however, try to incorporate this task during the training by, for instance, modifying the model structure. So, for instance, by formulating a model as a sum of univariate functions, you can check the individual feature impact on the prediction, or you can also add pairwise interaction, train on residual points. And our method falls into this last category of interpretability method because we will model we will formulate our model as a general weighted sum of several multivariate submodels, each restricted on a subset of interest. So our contribution are the following. We will propose a novel approach for attribution and show that we can have a fast algorithm to train them, and evaluate it on both synthetic and real data tasks. So prior to our method, there is an important hypothesis we make, which is that for real data, we don't have to consider the exponential number of candidates for the variable S. And for that, we leverage two ideas. The first one is group sparsity, meaning that we can often partition our input into coherent groups of feature, and we may only consider co-selection or co-deselection of those groups, and hence reducing the codomain of S to only 2 to the power the number of groups we consider. And the second idea is structured sparsity, meaning that we often have an idea of the sparsity pattern we will obtain, and we further prune the candidate space to only edge candidates. So in the rest of the presentation, we will work with only a reasonable number of possible submodels. So because we have a reasonable number, we can train actually 8 submodels, each restricted on a subset of interests. And the question is, how do we combine them to obtain a final predictor? So as mentioned, we'll use a weighted average that will be weighted by probability selection function that will be denoted by alphas. But how do we choose the alphas? Let's take a simple case. So imagine a problem that is bidimensional and we consider all the 3 possible restricted submodels. So 2 univariate functions and 1 bivariate function. As we want to use a minimal number of input features, we will either make a prediction using F1 that only use X1, F2 that only use X2, or F3 that use both input features. But we want to use F3 only in last resort, if and only if we cannot use F1 or F2. And to translate this else condition, we'll use boosting. So in particular, the selection value of F3 will be high if and only if both the selection of F1 and F2 are low. So this can be written in the general way as is. So alpha will be the product of a self-selection function, GS, times the deselection of all of the children. So children in the sense of including subsets. So in more detail, to implement this self-selection function in the binary settings, for example, and given a subset S, we propose to use a neural network with a codomain -1, 1, and that will be used for both the prediction and its absolute value will be used for to denote confidence. So other function can be used to control the error and confidence, but the overall idea is that the closer the prediction to either -1 or 1, the more confidence the submodel about its prediction. So I don't have much time to explain in detail, but this specific formulation allows us to emulate our H-restricted submodels into a single overarching neural network. And it all boils down to masking the neural network weights, which is really easy to implement and enables to reformulate many complex architectures like the transformer, recurrent neural network into interpretable ones. So of course, you can check the paper for more details and look at our GitHub. And the last step of our method is to train everything. So naively, we could train the submodels sequentially in a boosted manner, but thanks to the way we've defined our alpha functions, we can instead train them jointly using an EM scheme. So during the step, we will select the right submodels because that's a latent variable to select the right models. And then we will maximize the expected likelihood. But because we're dealing with neural network, of course, we can just perform a gradient step instead of perfect maximization. So that's a generalized EM scheme. So we'll evaluate our model with several tasks on the 2 objectives of completeness, so prediction power. Do we degrade the performances and interpretability? So are the attribution relevant? So here we just report the result of the sequential skip prediction for both the Deezer dataset and Spotify dataset. And the key takeaway is that the performances of interpretable models are closely related to the one of the non-interpretable counterparts, but that while selecting and restricting themselves to a minimal number of input features. Interpretation is more difficult to evaluate. So as you will see in the paper, we check that everything works properly on synthetic tasks for which we can compute ground truth attribution. But on real data, we can only check expected behavior or that we don't have a collapse on a certain submodel. And just to give you an example, so though it is cherry-picked, if you remember the skip prediction task in the introduction, we wondered if a prediction if we could distinguish between a musical skip versus an interaction skip. Well, this is exactly what our model allowed us to guess, because, for instance, in this session that is mostly a rock session, there is a sudden Malaysian pop music in the middle, and our model detected, highlight these changes, and predict a musical skip. So that's it. Again, thanks for your attention, and you can find more details on the paper and on the GitHub repository.
Thank you, Darius. We have time for some questions also this time. The first question is from Nava. How is this attribution explanation different from other kinds of local model explanations like LIME or SHARP?
Yes. So actually, it's not the same task we solve, because LIME or SHARP are a proxy task and often solve a local sensitivity interpretation, because basically they compute, or they're mostly gradient-based, they compute the gradient at a specific point, while the attribution task, as we formulate, is a bit more global. Because if you take the example of a XOR problem, so you have for regional space and the diagonal with opposite labels, it is typically a bidimensional problem. So the attribution, there is only one. It is that you have to consider the whole space. But if you use a gradient-based method, you can have very various interpretation values on the whole space. So that's a different task, also because we consider a restricted subspace. So it's just a different method, a different interpretation. But it's not opposite. We can use LIME if we want as a complement or in harmony with this method.
Okay. There's another question from Philip. You use output confidence for weighting. Is there an issue with overconfident predictions, a common issue in deep learning?
We did not observe that. So I think that's related to the fact that because the model are really restricted to a specific group of input features, if you have a bit of noise, because they have many data that is collapsed together, if they cannot predict, they will typically use a mean value. So if they don't know for a binary prediction, they will use 0 instead of -1 or 1. And because we have a joint estimation of both the prediction and confidence, this will translate as a null confidence, because you jointly predict, we jointly have a prediction and confidence. So that's why we avoid this effect.
Okay. There's one more question. I'm a little bit unsure whether that was answered before when you talked about LIME and SHARP, but what is the advantage of over post-hoc feature attribution methods like integrated gradients?
Yeah, so I think the difference is also in the fact that we are doing jointly the attribution and the prediction, while we're in integrated gradient or smooth grad or layer-wise propagation, you use a post-hoc model. So the model is not trained for the interpretation. You use one big multivariate model, and then, for instance, just consider one feature. So if you don't have a perfectly trained model, which is the case for instance, implicit signals, as we are dealing with, where we have an upper bound for the prediction task, because your model is not perfect, you can expect to have adversarial solution for the interpretation. And this is something that really happens with saliency methods, whereas where you use such submodels, because if you don't have the right attribution, because it's integrated into the training, if you don't have the right attribution, you don't have the right prediction. So it's more constrained, and it's more computationally expensive because you have many submodels at the same time, but you have more guarantees for your attribution.
Okay, thank you, Darius. Again, just a reminder, you can continue the questions on the QA interface in Moa. Now on to the last speaker of this session. It's Gustavo Pena from Delft. Take it away.
Yes. So hello, everyone. My name is Gustavo. I'm a PhD student at TU Delft. I'm supervised by Claudia Hauff, and this paper is about probing BERT for conversational recommendation. So first, I'll introduce conversational recommendation and also some related work. So here I have an example where someone who is seeking information starts the conversation by saying that he's looking for a 90s film with a great soundtrack. He says that he thought Power Rangers and Turbo were masterpieces, and he's looking for movies from that era with great music. He's looking for dramas, thrillers, road movies, and adventures. So someone who's providing information will give recommendations. So here in this conversation, he says that you should see Pulp Fiction or Rockstar, and this conversation goes on between those two people. So closely related to this is the field of natural language processing, and recently pre-trained language models, heavily pre-trained language models such as BERT, they have shown to be extremely effective at several NLP tasks, and they're extremely powerful for language modeling. The pipeline is usually the following: you train this language model with lots of natural language data and lots of GPUs, and then everyone can get this model that was pre-trained and fine-tuned for different tasks that of interest. And another related work has shown that such language models, they are also able to store knowledge in their parameters, in their weights. So for instance, if I want to know where the famous Dutch painter Rembrandt died, I could feed BERT with this sentence. So BERT died in the city of, and put a mask here, the mask token. And if I feed this to BERT, the highest output for a token will be for Amsterdam, which is the correct response. So in our work, we want to use the power of such heavily pre-trained language models for conversational recommendation. So we study here how does such models perform in such settings with probing tasks, and I'm going to define our probing tasks now. So we propose 3 different probing tasks. The first one is the genre probe. So here in this probe, we test BERT or on other language models if it knows the genres of movies. So for instance, if BERT knows already that Pulp Fiction is a drama and thriller, this could help during the conversational recommendation. The second one is the search probe. So basically here we test if BERT knows the content of the item, the recommendation item, and we do so by using reviews. So is BERT able to match this item title with the review? If so, in some reviews, it might be mentioned that the music of Pulp Fiction is really nice, and then this could also help us when we are doing conversation recommendation. So the last probe that we propose here is to test BERT for recommendation. So basically here, we want to test if BERT is able to match items that are frequently watched together or items that are frequently consumed together based on some user interactions data that we have. So here, if we have data saying that this is a set of ratings that occur often, it might help us as well for solving such tasks. If you know that Power Rangers goes before Turbo and then someone usually watches Pulp Fiction, this could be helpful. In order to do so, we construct prompt sentences because BERT receives sentences as input. So for the genre probe, we follow previous research and we generate close style prompts. So basically, we put the title of the movie here, and we say the domain of the item. So here, the Wind Up BERT Chronicle is a book of the genre, and then we ask to see if BERT knows this. We expect some tokens already because we have some databases telling us this. And we do the same for movies and music albums. For search and recommendation, it's slightly different because here we are comparing sentences with sentences and not sentences with tokens. So for the search one, we want to know if BERT is able to match the item title with the review of this item before the review of a random, before the title of a random item. So the relevant pairs should be ranked first by BERT. On the recommendation probes, we match together titles that are frequently seen together, and BERT should rank this relevant pair before the item with another, combined with another random item. So based on those sentences, we use some components of BERT to extract this knowledge out of it without doing any fine tuning. So we are interested in seeing what was already captured during the pre-training of BERT. So we rely on different heads that we're using during BERT pre-training and also the CLS token representation. We have more details on how we exactly do that on the paper. So our research questions are, first, we want to know how much knowledge does BERT have about such domains, about the items of such domains in the parameters. And the second is, how can we actually infuse some knowledge into BERT that could help us with conversational recommendation? So for the first probing we do is the genre probe. So those are the results already. So here we have the prior distribution. So if we only tell BERT that it's a book, it already is able to find some tokens that are relevant for this domain. However, if we actually tell the title of the book, we can get much higher performance with the probes. So this indicates that BERT does indeed have category information or the general information about such items in its parameters. This was our first probe. For the search and the recommendation probe, we saw that BERT has more knowledge about the content of the items rather than the collaborative filtering knowledge, which is to solve recommendation probes. So we see that it's more effective for the search probes rather than the recommendation ones. And since it's a language model, we kind of expect that to be true. So the next research question is about how we can actually use BERT to do this, to solve problem of conversational recommendation. So we use here a task that is to rank responses given a conversational context. So this is the context of the conversation, which is the history of so far of the conversation. So here we have like a conversation that goes like, hi, what type of movies would you like to see? And the answer is, I'm looking for something like Star Wars, but not Star Trek. And the correct response that the provider actually gave in this conversation is, have you seen Avatar? And we want to see if BERT is able to distinguish this response, the correct one, from negative candidates. The negative candidates, we use this as query to BM25 and use all the other responses as candidates. And here this is an example of that. And then we see if BERT is able to rank the correct one first. And here we are actually fine-tuning BERT for this task. And if we do so with actually fine-tune, we see that BERT is pretty effective in distinguish between the correct answers and the negative candidates. However, if we do a data set that's a little bit more difficult, if we generate adversarial candidates where we simply get this correct response here, and we just change the item that is being recommended to a random item. So this is now not a valid response anymore because we just selected a random item. It shouldn't make sense in the conversation. And if you do that, we see that there's a huge drop in the performance of BERT. So we see that BERT is actually easily fooled by examples that require it to compare different items or different movies, different books, and so on. So in order to improve this, and we have some more results on the paper, we actually train BERT also, besides for this task, we also train it for the probing tasks, we're using multitask learning. And on the paper, we see that we can improve this a little bit. And as future work, we think that it's important to think of ways to combine collaborative filtering models with language models, because we see that they need some help in that aspect. I think this, as future direction, we can also use language models for explainability. So give me an actual utterance explaining why I am receiving such recommendation. And also we could use this for other domains and other language models. So that's it. Thank you for your time. I will be happy to answer any questions.
Thank you, Gustavo. We have a few questions for you. The first one is asked by Bob. How sensitive is the performance to different phrasings of a probe? Did this differ by domain or genre?
Of different phrases of the probe?
Yes.
Yeah, so...
In the sense that different phrasings, so could...
Yeah, yes. So here in the paper, we discussed that a little bit. So this is only like a lower bound on what's stored in BERT, because if we use different sentences with synonyms, for instance, we could actually retrieve better scores. On the paper, we compare 3 different templates for generating the sentences. So it is sensitive to that. And there's also research being done into how can we generate better phrases, better templates to extract the knowledge from such models.
Okay, the next question is from Brian. Do we know if the query review texts were included in the BERT training data?
So this is something that we made a big analysis as to try to understand what exactly was in the pre-training data from BERT that could actually help us with the tasks, the data sets that we have. So, but the data that BERT was trained is not, we cannot access it easily, the exact same data. It was trained on Wikipedia in a corpus that has several books, so it's the actual content of the books. So this is, of course, very important to understand what the probes are. So the reviews, for instance, are not part of this data set that BERT was pre-trained on. And I think that was the question. So the reviews are not on the training data, but the books or the movies and so on, they can be part of the training data because of the Wikipedia pages and also the book corpus that it was trained on.
Okay, there's time for one last question from Justin. How do you think about approaching cold starting new items into a conversational recommender based on the models like BERT?
So I think that's actually pretty easy, right? Because in a conversational recommendation, you don't really have a history of ratings for the user. Usually on the problems, we only have what the user is telling us right now. So it's only the current information it's so maybe he mentions like 1 or 2 movies that he liked on the dialogue, and that could help the model to get a sense of this collaborative filtering knowledge. However, all other occasions are mostly cold start, right?
Yes, I would almost ask the opposite question. How do you include knowledge about the history of what a user has seen?
Yeah, so we try to do that by, say, telling BERT that what movies are similar with the probing test. So, for instance, we say that Lord of the Rings and The Hobbit is similar, and we train with a lot of different titles and see if this helps on the conversational recommendation task. So we actually train BERT using sentences. We tell it explicitly. So this and this item is usually watched together. And we can do that with several combinations to see if the language model is able to get that that knowledge into it. We had a little bit of success, but there's still huge way to go.
Okay, thank you once more, Gustavo. And a big thanks to all the speakers. Thank you for joining us to this session. And remember to check out the social activities over the next hour before the next session starts. See you around, and thank you very much.
Thank you all.